Let's now shift our attention to rotary vane compressors. Here you can see a cut view of a typical rotary vane compressor. And here you can see a 3D front view of the same compressor showing the suction side, and here the discharge side. Let's now remove one of the covers. As you can see here, a sliding vane rotary compressor uses a series of vanes that slides freely in longitudinal slots or grooves as depicted here that are cut into the rotor. Centrifugal force causes the vanes to move outward against the casing wall. The chamber that is formed between the rotor, between any two vanes and the casing, is referred to as a cell. And here you can see a typical rotary vane compressor in motion. As the rotor turns, an individual vane passes the inlet port to form a cell between itself and the vane that precedes it. As an individual vane rotates toward the end of the inlet port, the volume of the cell increases. The increase in the cell volume draws a partial vacuum in the cell. The vacuum draws the gas in through the inlet port. When a vane passes the inlet port, the cell is closed, and the gas is trapped between the two vanes, the rotor and the casing. As rotation continues toward the discharge port, the volume of the cell decreases. The vanes ride against the casing and slide back into the rotor. The decrease in volume increases the gas pressure. The high pressure gas is discharged out of the compressor through the gas discharge port. Sliding vane rotary compressors are characterized by a high noise level that results from the vane motion. The single-stage design of a rotary screw compressor depicted here consists of a pair of rotors that mesh in a one-piece dual-bore cylinder. The male rotor usually consists of four helical threads that are spaced 90 degrees apart. The female rotor usually consists of 6 helical grooves that are spaced 60 degrees apart. The rotor speed ratio is inversely proportional to the thread-groove ratio. In the 4-thread, 6-groove screw compressor, when the male rotor rotates at 1800 rpm, the female rotor rotates at 1200 rpm. The male rotor is usually the driven rotor, and the female rotor is usually driven by the male rotor. A film of foil is normally injected between the rotors to provide a seal between the rotor and to prevent metal-to-metal contact. An oil mist eliminator installed immediately downstream of the compressor is required for plant and instrument air applications. However, designs are available that do not require lubrication. Screw compressors that do not require lubrication are commonly referred to as dry screw type compressors. In this type of compressor, the inlet port is located at the drive shaft end of the cylinder. The discharge port is located at the opposite end of the cylinder, as depicted here. Compression begins as the rotors enmesh at the inlet port. Let's take a closer look at how this type of compressor works. Gas is drawn into the cavity between the male rotor threads and female rotor grooves. As rotation continues, the rotor threads pass the edge of the inlet ports and trap the gas in a cell that is formed by the rotor cavities and the cylinder wall. Further rotation causes the male rotor thread to roll into the female rotor groove and to decrease the volume of the cell. The decrease in the volume increases the cell pressure. Compression continues until the rotor threads pass the edge of the discharge port and release the compressed gas. Reciprocating compressors are perhaps one of the most spread rotating equipment in refineries, petrochemical, and process industries. Take a look at the following 3D animation. It shows how these special compressors work. The example that you will see here is a two-cylinder single-stage compressor. The basic components of this compressor are highlighted in this video. A prime mover, which is not seen in this video, rotates the crankshaft. The crankshaft converts the rotary motion of the prime mover into reciprocating motion of the pistons. The compression cycle of a reciprocating compressor consists of two strokes of the piston, the suction stroke and the compression stroke. The suction stroke begins when the piston moves away from the inlet port of the cylinder. The gas in the space between the piston and the inlet port expands rapidly until the pressure decreases below the pressure on the opposite side of the suction valve. The pressure difference across the suction valve causes the suction valve to open and admit gas into the cylinder. The gas flows into the cylinder until the piston reaches the end of its stroke. The compressor stroke starts when the piston starts its return movement. When the pressure in the cylinder increases above the pressure on the opposite side of the suction valve closes to trap the gas inside the cylinder. As the piston continues to move toward the end of the cylinder, the volume of the cylinder decreases and the pressure of the gas increases. When the pressure inside the cylinder reaches the design pressure of the stage, the discharge valve opens and discharges the contents of the cylinder to the process. Now, as discussed, the compression cycle of a reciprocating compressor consists of two strokes of the piston, the suction stroke and the compression stroke. For the following discussion, we will use an ideal indicator diagram followed by a series of cylinder illustrations depicting piston movement and valve position. So here you have the piston with the compressor cylinder. And here you have the suction valve, and here the discharge valve. The intake pressure or suction pressure is P1, and the discharge pressure is P2. The figure will show in diagram form one complete crankshaft revolution and will encompass a complete pressure cycle. To begin the cycle, the piston is located at the lower end of the stroke, also known as the bottom dead center. The piston, as depicted here, is at path point 1 on the indicator diagram. At this point, the cylinder has filled with gas at intake pressure P1. Note that the valves are both closed. The piston then starts to move to the left. This is the compression portion of the cycle and is illustrated by path 1, 2. When the piston reaches point 2 on the indicator diagram, the exhaust valve starts to open. At this moment, the discharge portion of the cycle starts. This is shown on the indicator diagram as path 2, 3. Note that the discharge valve is open during this period, while the intake valve is closed. The gas is discharged at the discharge line pressure P2. When the piston reaches point 3, it has traveled to the upper end of its stroke, also known as the top dead center. Physically, at this point, there is a space between the piston face and the head, as depicted here. This space results in a trapped volume of gas, illustrated in this example in red, and is called the clearance volume. Next in the cycle, the piston reverses direction and starts the expansion portion of the cycle. Path 3-4 shows this portion of the cycle. Here, the gas trapped in the clearance volume is re-expanded to the intake pressure P1. Note that the discharge valve has closed and the intake valve is still closed. At point 4, the expansion is complete and the intake valve starts to open. The intake portion or suction stroke begins. This is illustrated by path 4-1 on the indicator diagram. The cylinder fills with gas at intake line pressure P1. When the piston reaches point 1, the cycle is complete and starts to repeat as long as the reciprocating compressor is operating.